In this and in the next set of videos, I'd like to tell you about a learning algorithm called a neural network. We're going to first talk about the representation, and then in the next set of videos talk about learning algorithms for it. Neural networks is actually a pretty old idea, but had fallen out of favor for a while, but today it is the state-of-the-art technique for many different machine learning problems. So why do we need yet another learning algorithm? We already have linear regression and we have logistic regression, so why do we need neural networks? In order to motivate the discussion of neural networks, let me start by showing you a few examples of machine learning problems where we need to learn complex nonlinear hypotheses. Consider a supervised learning classification problem where you have a training set like this. If you want to apply logistic regression to this problem, one thing you could do is apply logistic regression with a lot of nonlinear features like that. So here, g as usual is a sigmoid function, and we can include lots of polynomial terms like these. And if you include enough polynomial terms, then maybe you can get a hypothesis that separates the positive and negative examples. This particular method works well when you have only, say, two features, x1 and x2, because you can then include all those polynomial terms of x1 and x2. But for many interesting machine learning problems, we have a lot more features than just two. We've been talking for a while about housing prediction, and suppose you had a housing classification problem rather than a regression problem. Like maybe if you have different features of a house and you want to predict what are the odds that a house will be sold within the next 6 months. So that would be a classification problem. And as we saw, we can come up with quite a lot of features, maybe 100 different features of different houses. For a problem like this, if you were to include all the quadratic terms, all of these even all the quadratic, that is the second order polynomial terms, there would be a lot of them. There would be terms like x1 squared, x1, x2, x1, x3, x1, x4, up to x1, x100, and then you have x2 squared, x2, x3, and so on. And if you include just the second order terms, that is the terms that are a product of two of these terms, x1 times x1 and so on, then for the case of n equals 100, you end up with about 5,000 features. And asymptotically, the number of quadratic features grows roughly as order n squared, where n is the number of the original features, like x1 through x100 that we had, and it is actually closer to n squared over 2. So including all the quadratic features doesn't seem like it's maybe a good idea, because that's a lot of features and you might end up overfitting the training set, and it can also be computationally expensive to have to be working with that many features. One thing you could do is include only a subset of these. So if you include only the features x1 squared, x2 squared, x3 squared, up to maybe x100 squared, then the number of features is much smaller. Here you have only 100 such quadratic features, but this is not enough features and certainly won't let you fit a data set like that on the upper left. In fact, if you include only these quadratic features together with the original x1 and so on up to x100 features, then you can't actually fit very interesting hypotheses. You can fit things like axis aligned ellipses like these, but you certainly cannot fit a more complex data set like that shown here. So 5,000 features seems like a lot. If you were to include the cubic or third order polynomial features, the x1, x2, x3, x1 squared, x2, x10, x11, x17, and so on, you can imagine there are going to be a lot of these features. In fact, they're going to be order n cubed such features, and if n equals 100, you can compute that you end up with on the order of about 170,000 such cubic features. And so including these higher order polynomial features when the original feature set n is large, this really dramatically blows up your feature space, and this doesn't seem like a good way to come up with additional features with which to build nonlinear classifiers when n is large. For many machine learning problems, n will be pretty large. Here's an example. Let's consider the problem of computer vision. And suppose you want to use machine learning to train a classifier to examine an image and tell us whether or not it is the image is a car. Many people wonder why computer vision could be difficult. I mean, when you and I look at this picture, it's so obvious what this is. We wonder how is it that a learning algorithm could possibly fail to know what this picture is. To understand why computer vision is hard, let's zoom into a small part of the image, like that area where the little red rectangle is. It turns out that where you and I see a car, the computer sees that. What it sees is this matrix, or this grid of pixel intensity values that tells us the brightness of each pixel in the image. So the computer vision problem is to look at this matrix of pixel intensity values and tell us that these numbers represent the door handle of a car. Concretely, when we use machine learning to build a car detector, what we do is we come up with a labeled training set with, let's say, a few labeled examples of cars and a few labeled examples of things that are not cars. Then we give our training set to the learning algorithm, train a classifier, and then we may test it and show the new image and ask, what is this new thing? And hopefully it'll recognize that that is a car. To understand why we need nonlinear hypotheses, let's take a look at some of the images of cars and maybe non-cars that we might feed to our learning algorithm. Let's pick a couple pixel locations in our images. So that's pixel 1 location and pixel 2 location, and let's plot this car at the location at a certain point depending on the intensities of pixel 1 and pixel 2. And let's do this with a few other images. So let's take a different example of a car and look at the same 2 pixel locations, and that image has a different intensity for pixel 1 and a different intensity for pixel 2, so it ends up at a different location on the figure. And then let's plot some negative examples as well. There's a non-car, that's a non-car. And if we do this for more and more examples, using the pluses to denote cars and minuses to denote non-cars, what we'll find is that the cars and non-cars end up lying in different regions of the space, and what we need therefore is some sort of nonlinear hypothesis to try to separate out the 2 classes. What is the dimension of the feature space? Suppose we were to use just 50 by 50 pixel images. That is, suppose our images were pretty small ones, just 50 pixels on the side. Then we would have 2500 pixels, and so the dimension of our feature size will be n equals 2500, where our feature vector x is a list of all the pixel intensities, the pixel brightness of a pixel 1, the brightness of pixel 2, and so on, down to the pixel brightness of the last pixel, where in a typical computer representation, each of these may be values between, say, 0 to 255. It gives us maybe the grayscale value. So we have n equals 2500. And that's if we were using grayscale images. If we were using RGB images with separate red, green, and blue values, we have n equals 7500. So if we were to try to learn a nonlinear hypothesis by including all the quadratic features, that is all the terms of the form xi times xj, well, with 2500 pixels, we will end up with a total of 3 million features, and that's just too large to be reasonable. It would be computationally very expensive to find and to represent all of these 3 million features per training example. So simple logistic regression, together with adding in maybe the quadratic or the cubic features, that's just not a good way to learn complex nonlinear hypotheses when n is large, because you just end up with too many features. In the next few videos, I'd like to tell you about neural networks, which turns out to be a much better way to learn complex hypotheses, complex nonlinear hypotheses, even when your input feature space, even when n is long. And along the way, I'll also get to show you a couple of fun videos of historically important applications of neural networks as well, that I hope those videos that you see later will be fun for you to watch as well.